here to give this course. As you already said, there will be 7 courses in total, each one's 3 hours. We're gonna break the courses in the middle, so it's like 1.5 hour lecture roughly, then there's a 50 minutes break, and then we have another 1.5 hours lectures. Roughly, that's the plan. The first lectures, not only are they taking place here in this room, but they're also more of an overview. So I try to be more general, try to give you less proofs, give you less details, but try more to convey the idea why we think the things that we are doing are interesting. Okay? And I guess the other thing I wanted to say is please ask questions. If you have any, I mean, that's what I'm here for. There's no fixed amount of material that we need to cover. If I can better answer questions, that's more important than that I cover the whole material. The lecture is going to be videotaped. I'm not sure when and where it will be shared with the public. If you don't like asking questions on the video, we will organize things like that. There are like 50 minutes at the end that are not videotaped. And if you prefer to ask questions at that point, please feel free to do so. Okay? So that's essentially my introduction. And now I will tell you what the Thirring inequalities are. And what are the open problems, the things that we know and the things that we would like to know. Okay? So, Thirring, perhaps I write it out for the first time. So Lieb is a mathematical physicist from Princeton, and Walter Thirring is, was a physicist in Vienna, and they proved a family of inequalities in 1975 that really have created a lot of interest and led to important questions both in physics and mathematics. And so that's what I will talk about, and from now on we will typically abbreviate this just by LT, just so that we don't have to write too much. Okay, good. So they had 2 papers, one in 1975 and then another one in 1976. And this 76 paper has already in the title Sobolev type inequalities. And so for the beginning of this course, I want to start with Sobolev inequalities. So there are different points of view that you can have on the Thirring inequalities. The basic view for today is the view of Sobolev inequalities. And I want to start with what is called a Sobolev interpolation inequality. So you have a function psi on Rd, d is my dimension. It's anything, 1, 2, 3, 4, 5, whatever. The physically interesting case that they mostly focused on is dimension 3, but actually we will see an interesting dimensional dependence. So keep in mind that we will look at arbitrary dimension. This is the gradient of psi. We assume that this gradient exists in the sense of distributions, and that the function is, that this distribution is a square integral function. And then there's an inequality that this integral controls psi to a certain power, 1 plus 2 over d dx. This inequality holds under a certain normalization condition, namely that the L2 norm of psi is equal to 1. Okay. Now, there's a certain exponent here, 2 times 1 plus 2 over d. That is not the largest exponent for which this inequality holds. Okay? What makes this exponent special? Right? There are such Sobolev type inequalities, right? So we're in the Sobolev space, meaning this and that is finite. So there is a whole range of powers for which we have a similar inequality. What makes this inequality special is that we bound an integral by an integral and not by a power of an integral. Okay, that is very important. in the nature of the Thirring inequalities and why they are useful. There's a unique such power where you bound the integral by that. You see by homogeneity, this is quadratic in psi, and this is psi to another to a higher power. So if you drop the normalization, you have to multiply by this term on the side. But for us, the usual thing is we assume this to be normalized, and what we're interested in is this locality, as we call it, right? That different pieces of psi contribute sort of equal to both sides. Okay, good. In the theory of nonlinear Schrödinger equations, perhaps you've heard that, that's what's called the mass critical case. It also plays a big role there. And so this inequality has many different names. Often it's associated to Gallardo and Nirenberg, who studied a general family of such inequalities. This particular one, I think in 2 dimensions, it's often called Ladishenskaya inequality. Other people call it Moser inequality because he used this in elliptic regularity theory. Whatever, I usually just call it Sobolev or Sobolev equation. But that's for the moment the best one. And finally, one word about this sign. I'm making this sign if I'm not interested in the constants. Of course, it's sort of understood that the constant is not allowed to depend on psi, but it is allowed to depend on the dimension, another dimension. Okay. Later on, we will talk about optimal constants and we will be more precise, but here I hope I can focus on more precise. All right, and now let me state this theorem of Lieb-Thirring. From 1975. So let's take any dimension. Any L2R orthonormal system psi n from 1 to n. So up there we had a single function. Now I'm taking many, perhaps I should be a little bit more for any n and any. So we have now an arbitrary collection. The length doesn't matter. You can think of it as being infinite or finite. Doesn't matter. So for any orthonormal system, we have the following inequality. Well, the left side looks pretty much like the left side up there. Just if I have n functions, I have to take the gradient of everybody, then sum it. And the point is that this can be controlled by, so what you do now is you take the sum of the squares of the functions, square them, and raise it to the power 1 plus 2 over d dx. And the key point here is, and that's what I mean by this statement, that this implied constant is independent of n. Okay, so it is a generalization of this Sobolev interpolation inequality to the setting of many functions. And the key thing is that these are not any n functions, but they're orthonormal. And because they're orthonormal, one can choose, that's the content of the theorem, the constant here independent of n. So let's just, forget. So orthonormality, just to be clear, so L2 orthonormal means integral psi n conjugate psi m dx is equal to delta m for all n. Okay? So in particular, it has this normalization condition built in. That's certainly what we need if we have a single function. And then when we have several, we have this orthonormality. Now let's imagine we drop the orthogonality. So just imagine we have a system of functions and each function is normalized by that. Right? Then I am allowed to take the same function n times. All right? And then this side, the left side, is just n times a number, while the right side is n to a bigger power, namely 1 plus 2 over d. So that inequality cannot hold with a constant independent of n. So if we drop orthogonality, we get a constant proportional to n to the minus 2 over d. But with orthogonality, we don't have it. You can put it differently. Orthogonality allows you to beat the triangle inequality. So let me say that again. It's a simple exercise. So again, drop orthogonality. Just apply here the triangle inequality to that sum. Right? And then you see that, so you apply the triangle inequality, then you apply this to each individual function, and then you see that the triangle inequality gives you a factor n to the minus 2. Okay? So it does not need to be always the same function, just the fact that if you don't have orthogonality, you have this power, and this power is sharp. But we don't want that power. And now what does this mean pictorially? So see, if you don't have orthogonality, then it means that all the functions can sit on top of each other, because they can all be the same. The opposite sort of says that orthogonality, in a weak sense, means that these functions have to go out of each other's way, right? So that locally they cannot pile up, but really, of course they don't have disjoint support, but in some sense they do. In the sense that the overlap becomes very small. And what I want to remind you, perhaps from high school chemistry, you've seen these pictures of hydrogen orbitals, these bubbles. And when you look at them or Google them on Wikipedia, you see, so there's the one S and then the second S wave, first P and so on. And when you see them, you see that they become bigger and bigger. So these are orthogonal functions, orthonormal functions. And you look at the pictures and you see exactly how they achieve the orthogonality by really spreading out over space. Right? In the usual chemistry models, perhaps you don't see the scale, but look at Wikipedia, you see that they become bigger. So this is really the effect that you see in these effective models in quantum mechanics, that you, of course I'm assuming, and this is true for the hydrogen orbitals, that this right side is bounded. So in order to have this bounded, they really have to go out of each other's way. Okay, that's this locality idea. That's the crucial point of the midterm inequality. Okay, good. This is going to be a mathematics course, obviously, but the motivation for these inequalities does come from the physics of quantum mechanics, and so I want to spend the next, say, 15 minutes trying to explain you the background. I touched on it already a little bit, but I just so that you know why people are interested in it. I will not emphasize this very much in the rest of this course, but at the beginning I thought I'll do something. So, if we have so this is now many body, so motivation from many-body quantum mechanics. So, state, pure state, if you want to be precise, of n d-dimensional particles, n particles in RD. Okay, so each, for instance in R3, right? So you have a particle that moves in R3. And now you have more than one particle, okay? Namely n particles, okay? Is described by a function psi, which is an element of L2 are d times n. That's sort of the people use the word curse of dimensionality. When you get more and more particles, the dimension of your space increases. Okay? And this makes the corresponding PE that governs the system, a Schrödinger equation, very hard or essentially impossible to solve. Because there are just no good numerical methods to solve PEs. Say n is 100 or something. When you're not talking about matter yet, we're just talking about atoms, or even molecules are much bigger, right? And so you cannot solve a PDE in such a large dimension. Okay? But that's what quantum mechanics says. We need to describe such a system, we need to go to this big dimension. Okay? There's one more thing described by that with psi. And let me be consistent, let's write this as a capital psi. And so the norm of capital psi in L2 of R2, Rdn is equal to 1. All right, good. And well, because this is so hard to imagine what it is, one often likes to look at simpler properties, and simpler properties are captured by the so-called one-particle density. One-particle density, and that is a function that's defined on Rd. So that's on the single particle space. Okay, and that's essentially the marginal of the capital psi, or more precisely, the sum of the marginals. So let me write this out. So you have lots of integrals, namely n minus 1 integrals, and then take a wave function, and at position n, you stick in the three-dimensional. So x is in Rd, said that already. So you stick that into the nth place, dx 1 through dx n minus 1, dx n plus 1 through dx n. So that's the integrals that we're doing. We're integrating out everybody except for the first particle. That's the usual marginal, but perhaps a little bit different from probability theory, that this is normalized to the n. Right? So note integral rho psi of x dx Rd is equal to n. So that's, I mean, it's a density, and it tells you how many particles you have, and more precisely, the integral of rho over region space is the number of particles you have in that region. Okay? Good. So, you know, the rho, you should think of the rho as something you can imagine, because this lives in our physical three-dimensional, d-dimensional space. Whereas this very high-dimensional thing, we cannot really imagine. Okay, good. So now we can associate to the state of kinetic energy. So kinetic energy of this state, just take it as a definition, is I mean, it's really a big gradient. It's just a gradient in this d times n dimensional space, but it's customary to write this as the sum of the individual gradients. dx1 through dx. We just take this as a definition. Quantum particle has a potential energy, which depends on the details of the potential, and a kinetic energy. That's the kinetic energy. Of course, there are discussions about relativistic effects and so on. I don't want to get into. That's a definition. Okay, good. So now we're almost there. The last thing that I want to do is that, number one, we're looking at particles that are indistinguishable. So that means that we have a certain symmetry in the particles. And now among indistinguishable particles, at least when the dimension d is large enough, there are different two kinds, namely bosons and fermions. And what we will be interested in is fermions, which are, for instance, electrons are fermions. Okay, so we are interested in fermionic particles. And so I write it here, for instance, electrons. And let me translate this immediately into mathematics. What that means is, this means that if you take your wave function and if you switch two coordinates, there's xn and the xm which sit at arbitrary places, then you pick up a minus sign. I hope you can read it. This holds for all m different from n. Or put differently, when you apply a permutation to the particle labels, what you get out is the sign of the permutation times the wave function. Okay, and so forget the name fermionic particles. That's physics jargon. This you can sort of forget. This is really what's interesting, and I will usually talk about antisymmetric functions. That means this property under exchange of particle moments. Okay, and then with this, I can state an equivalent version of that theorem, which looks very different when you haven't seen this before. So theorem, once again, Lieb and Thirring, 1975. Let d greater than 1. Then for any n and any L2 are dn normalized antisymmetric psi, we have the kinetic energy of this quantum state is controlled by the single particle density raised to the power 2 over d dx. Of course, I mean, very superficially, this looks similar, right? There's a sum over n, because I insisted that I write the full gradient in this way. And, well, there is a 1 plus 2 over d, which is the power that we have here, summed over r. Okay? And this superficial similarity, that is actually, even mathematically, a similarity, namely the constant, the best constant, here coincides with the best constant in the previous theorem. By this I mean that the two things really are the same. They're completely equivalent. If you can prove this, you get that, and if you get that, you can prove that. And that was sort of, several steps. So I go now with you through this 1975 paper from Thirring. As I will explain, this is what they were really interested in. And then the first reduction step is sort of, because this looks so complicated, let's turn this into a solar field. Okay? And then they say, well, this still looks complicated, let's turn this into yet another equivalence. But these are all equivalences. And so this is the first equivalence that we have. It's not obvious. I mean, sketch one direction. So, I don't know. I'm not a big fan of labeling theorems, because I always forget the labels, but let me do it nevertheless. So I put a 1 there, and I put a 2 here, just so that you know what we mean. I mean, this is just for today. Okay, so argument, a proof, theorem, which is it? I want to say 2 implies theorem 1. Just so that you get an idea of the equivalence. Of course, the harder part is the opposite, which was what Thirring were interested in. But what you can do is, if these psi n's are orthonormal, or psi n orthonormal, we can define a capital psi in the following way. So you build a matrix which has entries labeled by n and m. And so the n and m run from 1 to capital N. That's a square matrix. Of this matrix, we take the determinant, and then we multiply by a normalizing factor. All right, now let's look at this thing. So one thing which is hopefully clear is if you switch, sorry, and I'm not being consistent with my notation. I wanted to use capital X's for the many body level. Okay, so if you switch an xn and an xm, you see just from the antisymmetry of the determinant that you get a minus sign. So antisymmetry is good. Good. Now, next thing is that I want to compute the density of this capital psi. And this is a computation, but it's an equality. You know, you set down, I mean, you write the determinant using this formula of the sum, and then you plug it into this definition of the density. Where is it here? It's down there. And then you see that there are lots of, there are squares, and there are lots of terms that cancel each other because of orthogonality. Okay? And so when you do this, at the end of the day, you see that you have this pointwise equality. All right? And that proves several things. So this implies in particular that the norm of this capital psi is equal to 1. Because the norm of the capital psi is the integral of this divided by n, and this thing has integral n. Okay, so this you get out. And then the last thing that's a similar computation is that the gradient, the kinetic energy, as we call it, of the capital psi dx1 dxn is equal to the sum of these individual kinetic energies. It's a similar computation. Again, the formula for the determinant, you differentiate, right? I mean, it's a product, so the derivative hits one of the terms in the product, and then you multiply out, and by orthogonality you kill many other terms, and what remains are the diagonal terms. And you see already, I mean, there's some number of permutations in there, and that explains why I had to put the 1 over square root of n factorial. That's exactly the number of permutations. Anyway, so that's a brief sketch of how this argument works. And of course, the interesting thing is the opposite direction, namely saying that if you have a capital Psi, then sort of the best you can do is replace the given capital Psi by something like this, okay? Or at least a convex combination of such things. Okay, but that we will talk about this later. Yes, please.
Yes, just how people think about that function? Phi.
This one, this is the physics name for this is a Slater determinant. And the idea is that non-interacting system of fermions have a ground state equal to a Slater determinant. So sort of in a regime where you think that the interaction between the particles are weak, you expect these to be good guys, or close to optimal guys. Okay? But anyway, so I'll be more, later on in this course, I'll explain the other implications, but for now I hope I've given you at least some sense of why these two theorems are connected to each other. Okay, now let me move on and let me tell you what Lieb and Thirring were really interested in, this problem of stability of matter. Okay, and then I go through that, and then we are sort of, at least for the moment, done with the physics background, and we concentrate back on the original. So let's talk a little bit about stability of matter. And so what that means is that, well, ordinary matter, and by matter I mean really a table like this or a chair like that, that this is, or water, is not very exciting. I mean, namely, just if you have two bottles of water and you pull them together, then you have twice as much water. Nothing interesting happens. Okay? So just you put matter together and, well, it stays matter. Now, why does this require proof? Imagine you have n particles in there, and you know, huge number, 10 to the minus 20, 30, particles together, 10 to the 20, 10 to the 30, you put it together, you have twice as many particles, but if you think about every particle interacts with every other particles, then the number of interactions has become the square, whereas sort of the energy has just become twice the energy, it's linear. Okay, so there is, that's the sort of the paradox of the thing that we need to explain. Even though there are many more interactions, the energy just doesn't, like, just behaves linear. Okay, so there's a huge cancellations between positive particles in there and negative particles. Okay, there are all the electrons and the protons and neutrons, and some of these interactions are come with a plus sign, some with a minus sign. And what we need to understand is this precise cancellation so that at the end of the day there's just a linear. Okay, that's the physics. I go to mathematics, I try to explain it. Okay, so we have what's called the Coulomb system. And that's composed of n electrons described as we just discussed above, described by, so L2 normalized, antisymmetric, psi. That's what we do. Now we have nuclei, k of them. Those we do not treat quantum mechanically, or rather we treat them as fixed points. Okay, just because they're so much heavier than electrons, we do not take their kinetic energy into account. I mean, that would give actually positive terms, so it would make life simpler, but it's such a small positive term that it doesn't really have very much. but we do classically optimize on the positions. So at positions R1 through Rk, these are points in R3 with charges Z1 to Zk, and I suppose that these are arbitrary positive numbers. You know, charges really are quantized, but in this theory that I'm doing, this does not play any role. So let's just take these positive numbers. Okay, good. So that's what this system consists of. Now let me write down an energy functional. Energy. Okay, so that is the energy. It depends on the positions of the nuclei. R is sort of the vector that consists of all these R1, R2, and so on, and the vector of charges. And my many-body wave function that we talked about before. Okay, now here we go. This is a huge integral. Let me RD. Okay, good. Now, first of all, we have the kinetic energy of each particle. That's the term we talked about. Good, that's what we have. Now, every particle is attracted to every nucleus. Okay, so minus for an attraction, and now there is the sum k from 1 to capital K, Zk divided by xn minus rk psi squared. Okay, so this is the electron nucleus attraction.
D equal 3.
D is equal to 3, right? And it's a Coulomb system because we're describing this interaction in Coulomb forces. Okay, now, next thing, the electrons are negatively charged. 2 electrons repel each other. Right, so what I have to do, this comes with a plus, and this is now n, a 1, less or equal n, less than m, less or equal than n, 1 over xn minus xm. Psi squared. This is the electron-electron repulsion. Now there's a last term which I need to include. I could write under the integral or not, but I prefer to keep it outside. So this is 2 nuclei. They are positively charged, so they repel each other. So I also have to take that repulsion into account. And that comes with a factor of Zk, Zl divided by Rk minus Rl. So that is the energy of this Coulomb system. Here it is. It's quadratically psi. That's what I mean. Psi is normalized, right? So if you want to have it homogeneous, you can multiply by the number of psi. Okay. And now what are we interested in? We're interested in minimal energy configurations. So ground state energy is E or Zn, that's defined to be the infimum of E or Z psi over all L2 normalized antisymmetric psi. And you know, implicitly I'm assuming that these psi are in the right Sobolev space so that this is finite. If they're not, then I interpret this as plus infinity, and I mean, it's still true, but I just don't care. Okay, so that is the thing that we care about. That's the ground state energy of such a Coulomb system. And the thing that I described when we had this example with the water bottles was that the ground state energy, which is negative, should be bounded from below by minus the total number of particles to the power 1. And not to the power 2, even though the number of interactions are the square of the total number of particles. Okay? And that is this theorem, which is due to Dyson and Lenard. So they were, I think, among the first ones to raise this question and answer it at the same time in 1967. And then Lieb and Thirring gave an alternative proof of this Dyson-Lenard theorem in 1975, and it's this proof that relies on all this machinery that I told you about so far. Okay? And now what is this theorem? The theorem says that E or Z n is bounded from below by minus. Now there is a constant, and usually I think I write it as 2z plus 1 times n plus k with z defined as the maximum of the charges. I mean, just the worst cases. Think about all the charges being equal. That's what you should think of. So now, and sorry, this should be scale. So, I mean, actually don't look too much at the charges, you know. I mean, when we have water, so the charges are just in a finite list. The interesting dependence that you should care about is n and k. These are the number of particles in the system, and we have the law that this goes like the power 1. Okay, that was what they proved and what is referred to as the vertical. Yes.
What do you expect the energy is negative or something like that?
Why? Well, just because, I mean, this term wins so much. I mean, think of it classically, right? When you would, then the energy would be minus infinity, because you can just put the particle on the nucleus. And then this term wins, is minus infinity, and the other terms are not. I mean, a single particle at the nucleus makes it already minus infinity. Now, the sort of the uncertainty principle says that you cannot put the particle exactly at the nucleus. So the uncertainty principle, that's the gradient that helps you. So it's not minus infinity, but it cannot make it very big. So that's the very rough explanation. But I think more to the point, I think you can just spread out the state. I mean, just take a psi that is just scaled down. You know, I mean, L2 invariant scaling, and then you see that the energy of such a state is equal to 0. Okay, and so therefore the energy is lesser than 0. But so that's a simple mathematical question.
Sure. How about the proof of Dyson and Lenard? What tool did they
okay,
use?
So it's. I mean, of course, what makes the theorem work is the antisymmetry, and they also use the antisymmetry. So I think what Thirring accomplished is that they were able to put the main idea of the proof into such an elegant inequality that has its own mathematical life, and that's an important, very important thing as well, that Lieb and Thirring were able to make the constant much smaller than the Dyson-Lenard constant. So the Dyson-Lenard constant is something like 10 to the 14 or something. So that, whereas the Lieb-Thirring constant is something like 2. I mean, it's, and you know, I mean, there is a natural energy, there's one Rupert, that's the energy of a hydrogen atom. That's what we should compare it to. And that's what we think, I mean, that's the order of magnitude the energy you should have. And a theorem where you have a constant like 10 to the 14 is physically not really. And so that was accomplished, this huge decrease of the constant was accomplished by putting it into this allegate form. Okay, but now, I mean, to be fair, one should say that nowadays people have revisited the Dyson law procedure, and there are situations where this is a very powerful technique that is helpful. So it's, I mean, it should not be completely discarded. And plus, they have raised the whole attention of the mathematics community to these questions. Okay.
This question, I think it's a very natural question. Do you also have an orthogonal?
I would imagine it's of that order, of the same order. I mean, of course, sort of.
Because apparently this doesn't say that your energy scales linearly.
You're absolutely right. But you know, so I mean, one point of that bound is that it does not depend on the positions of the nuclei, where you spread them in series. But you know, when you spread them very far apart from each other, you can just take at each nucleus, you can just make it sort of asymptotically neutral, and then you can get that out. I mean, sort of trivially, just by taking everything very far away from each other. So therefore, the infimum of this with respect to R is certainly that order, by making this corresponding function. But thanks for pointing this out. Exactly. It's in these problems always that lower bounds are the more important ones, because then we have to control the energy of any state. Mm-hmm. Whereas in order to get an upper bound on an energy, we just have to find a good configuration, which, I mean, is computationally perhaps hard, but at least physically we would know what to expect. Thanks. Any other questions?
Give some intuitive explanation why the constant just depends on the maximum of the charge. I mean,
no, so I'm not claiming that this dependence is optimal. That is, I did not try, or people have not tried, or works that I'm aware of have not tried to optimize this. This is just to get something. And it's a very cheap argument. So there will be a one-line proof saying, without loss of generality, we may assume that all of them are the same. And that's at the beginning of the proof, and then we don't care about that anymore. But, you know, I do not know what to expect in certain extreme regimes. But thanks for pointing that out. Anything else? Please feel free. No? It's good. Okay, so what should we do now? So I have about 40 minutes left before the break. So I would, if you don't mind, I would go through the proof of the stability of matter. I mean, really, so just let's stick to that for a little bit more. Do that, and then in the second part of the lecture, we return to this thing up there. Okay. I mean, I know that I also need to prove the Thirring theorem itself to you, but sort of for consistency, because now we've spent the last half hour talking about this, it might be good to stick to that, and just so that we get an idea of how to use that. Okay, is that fine? We do that. And then we move to the board first. I mean, there is a huge literature on stability of matter. Lieb has worked on this problem for many different systems. There is a book by Lieb and Thirring, if you want to read more about it. The background, you know, I'm just touching it very superficially, and I'm going sort of straight to the proof, but really to do the topic justice, one would have to speak much more about it. So let's look at the book. If you want to learn more about this, it's very pedagogically presented. requires essentially no physics background, has all the mathematics in there, and then of course there are also enough review papers on this topic. For instance, for Lieb's 90th birthday a couple of years ago, we had a 2-volume book series edited where different people describe different contributions of Lieb, and these things that are presented here also feature in this with several articles where you can find background and more modern developments. Okay? But so, right now, let me talk about the proof of stability of matter. And so what we need is one more inequality beside the Thirring inequality. The second inequality is, I would say, simpler and significantly less deep than the Thirring inequality, but we do need it. Let me begin with, so that's electrostatic inequality. And so one version of that is due to Baxter in 1980. So the original Thirring proof was 75, that did not go that way. Okay, but what I'm telling you is perhaps more direct. And so what's that? So that's an inequality about classical particles. So what do we have? We have the electrons and the nuclei, which repel each other. And see, now I'm already looking at equal charges. So there's this minus, so they attract each other, that's the minus sign here. Then you have the electrons that repel each other. And then we have the nuclei that repel each other. Okay, and so this is a classical Coulomb energy, right? There's no wave function psi, no kinetic energy. It's just n plus k particles that interact in that way. That thing can be bounded from below by minus 2z plus 1 sum 1 over delta r xn, n from 1 to n. Now I should tell you what that is, with delta r of x defined as the minimum of k of x minus rk. Let me tell you what that is. On the left side, you have this complicated Coulomb system, where you have many interactions, everybody with everybody else, some positive, some negative, which is complicated. On the right side, you have something rather similar, rather simple. Okay, you have just one-body interactions. Just each particle has a certain, there's a certain attraction to a fixed set R, okay, the set of nuclei. So each particle, each electron just interacts with the closest nucleus. Okay, so if it switches, there's one, there's another one. Here it just feels that one. Here, if it goes there, it just feels that one. And so it moves through space and only sees a single nucleus. And all the other interactions between the nuclei, between the electrons, they've all disappeared. Okay, so therefore this thing is much simpler. And so what we'll do is sort of then we'll plug this into that inequality up there. We will replace this, that, and that by this interaction. And then this problem we will be able to solve using the Lieb theorem. That's sort of the main thing. Now, we'll talk a little bit about that inequality. Improved by Lieb and Yao. See, what did Lieb and Yao not like? This is H.T. Yao. What did Lieb and Yao not like about that inequality? They did not like the 2. Right? Because so your electron goes through space, sees its nearest neighbor, and then the inequality pretends that now this nearest neighbor, this nearest nucleus, has twice the charge it really has. So that factor 2 sort of is not really intuitive. Because I mean, if it's closest to that guy, it should see essentially only that charge. And for problems, I mentioned this before, when you take relativistic effects into account, then the charge really doesn't matter. That's just because the relativistic kinetic energy scales in the same way as Coulomb, so you have the two things scale the same, so constants matter, and then the factor 2 would kill. Okay, and so the improvement of Lieb and Yao gets this with essentially 1 plus a lower order terms. Now what I'm going to present to you is another proof, which is worse, which has a much worse constant than that. But on the other hand, the advantage of my proof, it's not my proof, but it's a proof that I adapted from work of Pfefferman and Delayabe. The advantage of that proof is that it does not rely too much on the Coulomb nature of the interaction. Okay, see, what Baxter and Lieb used very much is that the function 1 over x is harmonic in a 3 outside of the origin. And that you have there you have a delta function which has a sign. Okay, that's really crucial for this. The argument that I will give you in a little bit works for much more general class of interactions at the expense of getting a Bose constant. Okay, anyway. So that's that. But before I give you this proof, I will explain how using this inequality and Lieb Thirring you get stability of matter. Okay. So from Lieb Thirring plus electrostatic to stability. All right, so we take our energy in the state psi. And now what do we do? Well, over here we have the Lieb Thirring inequality for the kinetic energy, right? So we can replace that by an integral over Rd times, now I'm giving this Lieb Thirring constant a name, I'm calling it K3, that name will appear later, and then we have the rho psi to the 5/3. Right, when dimension is equal to 3, 1 plus 2/3 is 5/3. That's this inequality that I'm using. Just gave the concept. And then I have minus, now I use that inequality here, so that gives me a 2z plus 1. And then you see, so I plug this thing in there. Now look at the nth term, fix n, and then you integrate out all the other variables of the psi. But that gives you exactly the density. Right? That's what the density is the marginal, and when this depends only on one variable, then this thing here is just 1 over delta R times rho psi of. That's the advantage that I have here, just a one-body interaction. And I can write it completely in terms of row psi. Now, what we want to do is, roughly speaking, use Hölder's inequality. Because we have a 5/3 in the positive direction, and here we have a smaller power in the negative direction. Okay, now that would give us the Hölder dual of the 1 over delta, but that unfortunately is not quite finite. So we have to do one more trick, which is easy. And I will introduce a certain cutoff. 2z plus 1 over delta r. And so I put here a minus mu, I'm doing this right, rho psi x, and then a minus mu n. Just confused with the signs, but I think that's right. So, I mean, so first of all, this is an identity. Where does the mu is a number, an arbitrary number that we will choose later. What did I use? I only used the fact that the integral of rho is equal to n. Okay. Now, why did I take this mu parameter? That will provide a cutoff of that. Okay. So, what exactly does that mean? This means now I do my Hölder inequality. Okay, so K3 integral R3 rho psi to the 5/3 minus, now what? Integral 2z plus 1 over delta r minus mu. I'm just using the positive part, right? I mean, this function is a positive part and a negative part, but because of the minus sign, only the positive part is relevant, and the other one I can throw out. And then I'm using a Hölder's inequality. The Hölder dual of 5/3 is 5/2. 2/3 plus 3/5. 3/5 plus 2/5 is 1. Okay, so this is 5/2, 2/5. Integral rho psi to the 5/3. All integrals are odd. To the 3/5, and then minus mu n. Good. Now we're almost there. So now what you see is an expression. So we don't know what this rho to the 5/3 is, that integral. But we see it here and we see it there. And so now what we use is a simple inequality that if you have x minus, what is it, a to the 2/5, x to the 3/5, then this is greater or equal to minus a constant times a. Okay, that's, I mean, you can scale out a, and then it's, so just by scaling, you can replace x by x divided by a, and then this just says that the function x minus x to the 3/5 is bounded from below. And of course, I mean, we all know how to compute that constant, and then we would get constants out at the end. But now just, I want to drop this, okay? I don't want to talk about constants for the moment. Okay, so we use that inequality, that simple inequality, and we find that this is greater or equal than minus a constant times the integral over R3, 2z plus 1 over delta r minus mu, positive part 5/2 dx. That's this first thing, and then there's minus mu to the n. All right, now what we do now is I claim that this integral here is 1 over delta r minus mu positive part to the 5/3, 5/2 dx is equal to, let me look at my notes. That's a scaling argument. 2z plus 1 plus 1 mu to the minus half. 2z plus 1 to the plus 3 mu to the minus 1/2 integral of 3 1 over delta r tilde minus 1 positive part to the 5/2. For some r1 tilde rk tilde. And so this is just scaling. I know that, I mean, I'm jumping over several steps here, but you can imagine, I mean, this delta function, like the Coulomb function, potential, that's homogeneous. So therefore, you can multiply, when you multiply x by a certain factor, then you eventually just multiply the nuclei by a certain factor. Okay? And so in this way, I can achieve two things. Namely, I can achieve that the mu becomes 1, and I can achieve that the charge becomes 1. Okay? And they come out with certain factors. So just do that computation. You can also do it by dimensional analysis. So the delta, that's the delta is a length. So you count, I mean, with how this is dimensionally related to that, and you take the 5/2 power into account and the dx, and then there's only one way you can do that. Okay, so let me not go too much into that. What we will do now is simple bound, almost there. So what is this? Remember, delta was the distance to the nearest nucleus. Okay, so delta was an infimum, but here it's a 1 over delta, so this is actually a maximum of 1 over x minus r tilde k minus 1 positive part to 5/2. Now we do something rough. Instead of taking the maximum, we just take the sum. I don't need to decide which one I take. Take all of them. And now we plug that into the integral. Now for the integral, you see that, I mean, just by translation variance, each term in the sum gives you the same contribution. Okay? And then there's an integral left. So I need to tell you what is that integral. The integral you have to do at the end is 1 over y minus 1 positive part to the 5/2 dy. Okay? So let's look at whether this integral is finite. So at infinity, y is very large, so 1 over y is very small, so this does not contribute because of the 1. That's why we introduced the mu in the first place. Okay? So there's no infinity, and if we look at small y's, well, then 1 over y is very large, so the 1 is sort of irrelevant, and the singularity is like 1 over y to the 5/2, and in 3 dimensions this is integral. Okay, so this gives you a finite number, which again you can work out. You will not do the computation now, and so you plug this in, and then you find that this whole integral is equal to a constant, that is 2z plus 1 power 3, mu to the minus 1/2, and then times k, because the only dependence on the nuclei is the k coming from the sum. So summary. The energy of any state is bounded from below by minus a constant times. I'm continuing here. Times 2z plus 1 or 3 mu to the minus 1/2 k minus mu times k. And this parameter mu is still at our disposal. So we're going to choose the mu in such a way as to make this as big as possible, right? Because we want to find a lower bound. So choose mu equal to a constant times. Now, right, so I multiply mu. I just want to balance the two terms. It's mu to the 3/2 is equal to k over n. 2z plus 1 squared times k over n to the 2/3. And then we get the energy, or z of psi, is greater or equal than minus constant times 2z plus 1 squared, and then we have k to the 2/3 n to the 1/3. I hope you can read this. It's k to the 2/3 n to the 1/3, and of course the important thing is that 1/3 plus 2/3 is equal to 1, so this thing can be controlled by n plus k. Okay? So I just write it here. Note k 2/3 n to the 1/3 is controlled by n plus k. In this way, we've proved our stability of matter. We have found the linear lower bound on the energy. And of course, the crucial, there were two identities here, namely the Lieb inequalities here, namely the Thirring inequality that we used at this point, and then there was the electrostatic inequality, which we also used here. The rest was rather simple manipulations, so what I showed you was rather a reduction to these two ingredients than the actual proof. It is noteworthy, I think, that if you follow this proof and do all the computations with all the constants, then you get a constant that's of the right order of magnitude. It might be too big by a factor of 3 or something, but it's in the physical range of constants that we allow. Okay. I should give credit here to Soloway, who I think in some proceedings had essentially this argument. I don't have it here. Soloway, yes, it's an article called Stability of Matter from 2006. Okay, good. I will now tell you about the proof of this electrostatic inequality. Okay? And then we will have the proof.
When you bound the max over k for all,
yes.
Could you, if you, I don't know, would it be possible to have a clever argument to have a better dependence on k?
I don't know. I think people are sort of excited about every little fraction that you can save to the arguments. If you can save a factor of, I don't know, 0.2 or something, then I mean people would be excited. I mean, try it if you have some ideas. I know it looks rough when one looks at it at first sight, but it is worth trying. And so far, I mean, perhaps you've seen this in this outline of the course so far mostly ignored constants. But now in the second part of today's lecture, I will talk about constants. They will then play the key role. And so, but before I go there, I wanted to show you why these things are useful. Okay, but keep in mind that eventually we will care about constants and that there are important, mathematically and physically important questions about these constants that I'm going to tell you later today. Okay, good. Electrostatic inequality. Lemma. So I told you I will do it for general Riesz potentials in general dimensions. So to emphasize that this proof that I'm presenting has nothing to do with it. Then minus, so it's a sum over n's and k's. There's a z, again all charges are the same. I guess I didn't tell you in the previous argument why I took the z all equal. I can, if you ask questions, I can answer that later, but let me not get distracted. Now, so now I take an interaction which has a lambda there. Okay? It's a lambda that makes this locally integrable. As before, I have repulsion between the particles, x first, xn minus xm, with the same lambda, and then I have a repulsion between the nuclei. So, Rk minus Rl. The claim is that this can be bounded from below, so there's again this 2z plus 1, which comes out with power 2, and then there's a sum n from 1 to n of these one-body interactions, exactly the same as those we had before, except that now the homogeneity, there's a lambda. And I want to prove that to you. Okay. So the constant, the implied constant, depends on lambda and d. That's what I mean by this period here, but it does not depend on the x's and the r's. I told you that this proof is inspired by a work of Pfefferman de la Llave that they did at the end of the 80s. And Charlie Pfefferman. And here's the formula, which is a beautiful piece of mathematics by itself, completely elementary, but very powerful. So this is the interaction, okay, between x and y with a power lambda. And I can write this interaction between a particle at x and particle at y in terms of balls. What do I mean by in terms of balls? By this I mean centers of balls. I'm doing the integrals first so that it becomes a little bit easier to read. So the a's are the centers of the balls, and then the radii of the balls. dr divided by r to the d plus 1 plus lambda, the characteristic function of where the x is in this ball times where the y is in the ball. It's a crazy, crazy thing, right? So you slide of all balls that you can think of on Rn, any in the center, any size. And then you just take the interaction to be 1 if both x and y happen to be in that ball, and 0 if not both are in the ball. Where does this come from? When you see this for the first time, it's really amazing, but it's actually just scaling, right? Because, I mean, see, what is special about the left side? The left side is, so first of all, it only depends on x minus y. Secondly, it only depends on the distance, the length of x minus y. And thirdly, it scales with a certain power if you multiply x minus y by a power. So let's check that the right side has the same properties, and if it does, plus if the integral is finite, then such a constant exists. Right? Because this is the unique function that has these properties. Okay, now let's do translation variance. Let's say I move, I guess if I move both x and y by a certain amount b, well, change x and y by an amount b, what are you doing? You're just changing the center by an amount b. But since you're integrating over all centers in a homogeneous way, this is invariant under that. Okay, now the next thing is if you rotate, so now we can think of x minus y as one variable. Or in other words, we can put the y equal to 0 and just look at x. So now just rotate x, right? But then see, what am I doing? You can, so there's a rotation of the x, which again you can put as a rotation on the center, and then you can absorb and here's the 0, so you can put the rotation on that center for free. And then you can just use the rotation invariance of the dA to say that this is rotation. Okay, and the last thing you do scaling, that's also easy, because that's a d-dimensional integral, so that's length to the power d. That has an r to the d, so that divides out the length to the d. There's an r to the power 1, that divides out the dr. Okay, and then what's left is only a length to the power lambda, which is exactly the homogeneity here. Okay, and so the last thing you have to do is just making sure that this integral is finite. And then you look, just like we did before, you look at the singularities. As this point, it's 0 and that infinity. Okay, so that's a very beautiful and powerful formula, and we do not need the value of the constant. That's actually a good calculus exercise to find that, I can tell you. But that value of the constant will determine that. So it's in principle explicit, but you have to sit down. Okay, good. So how can we use this? Well, we can write the left side now. Left side is equal to. Well, there's the funny constant. There's the dA, there's the dr over r to the d plus 1 plus lambda. Okay, good. And now what do we have? Well, we have the sum nk with a minus sign, z over, no, minus z, and now there's a 1 BRA xn, and there's the 1 BRA RK. Next, there's the plus sum n less than m, BRA xn 1 BRA xn. Next, plus z squared sum k less than l, BRA RK BRA RL. That was a lot to write, but it simplifies soon. Namely, right, I just plugged these terms in there. Okay, good. So now I want to rewrite this. And I'm saying that all this thing here, yep, there's these, did I own them? The nuclei have charged z, so you're the charge z. Okay, good. Now that's easy here, because in the first term we can carry out the n sum. And so what do? We just count the number of electrons in that ball. So I'm going to call that NRA. NRA is equal, by definition, the sum of the xn in this ball, which is just the number of n such that xn is in the ball. I'm going to define K or A similar. So right here we can do the K sum as well. Now here we need to think a little bit, because here there's this constraint that every particle interacts with every other particle, but not itself. So if you work this out, what you get is plus 1/2 NRA times NRA minus 1. You see where this comes from? So if you look at the NRA squared, right, that is everybody interacting with everybody else. So which error did I make? I counted the self-interactions. And what are the self-interactions? That's exactly when the ball hits the same ball. So that gives the -1 here. Okay, so n squared, that's n squared. That's everybody with everybody else. The -1 takes care of the diagonal interactions, but then we've still double counted, because we've counted each pair twice. There's an n with m and an m with n, and that's this 1/2. Okay, good. Let's continue. For K, it's the same story. There's a KRA times KRA minus 1. Now here's a simple computation. Where did we have that? Use minus Z and K, perhaps I'm not sure this needle, plus 1/2 N minus 1 plus this squared over 2 K times K minus 1. This thing is greater or equal than minus, how will I do this? Z plus 1/2 times n times the characteristic function for the K is greater than 1. That's elementary. That's for any, that is true for every n and K. I mean, I guess when I tell you that it's true, then you can verify it. Essentially, you break the proof into two pieces, namely, so you optimize over K, treating K as a continuous variable, you find the minimum, and then when Z is sufficiently large compared to N, then this is good enough, and otherwise you see that integer effects come into account, and then you have to treat the other case separately. But that's completely elementary. So just, you have that, and I'm using it down here. So, left side is greater or equal than minus the constant into dA, dr on to the d plus 1 plus lambda. Now what? Let me put that outside. 2 minus constant times z plus 1/2. N, that was the NRA, and the characteristic function of where the KRA is greater than 1. What is our goal? Our goal is to bound this complicated many-body interaction by sums of, one-body interactions. Okay, so we want to get the sum on n out. Well, that we can do right away, because the n is a sum. Okay, so I'm unfolding the n. I mean, perhaps I should have emphasized, I mean, this is a key thing, right? This is sort of even though it looks elementary, you see here you have the many interactions. There's an n squared, there's a k squared. That's where the interactions are quadratic in the number, whereas here they're only linear. There's a lot going on in this inequality. It's an inequality about numbers. And you can verify. And, you know, I mean, as I said, you just optimize with respect to k. And that deals with essentially everything. So once we have that, we have our n here, our single particle, r to the d plus 1 plus lambda. So this was where the xn sits in this ball, and then the characteristic function kra is greater or equal than 1. Good. Let's bound it. We're almost there. I'm saying this is less than, well, the first term I keep, not doing anything. And the second term here, I'm bounding by its time that this nearest neighbor interaction comes in. drxn is smaller than 2. Where does that come from? Let's talk about that. Right, the left side is a product of characteristic functions. The only important thing is when the left side is 1, the right side better be 1 as well. Okay, so left side is equal to 1. What does that mean? That means xn is in the ball around a of radius r. And it also means that there is at least one nucleus in this ball. Okay, so and there exists a k such that rk minus a is less than r. But if I have these two properties, then naturally xn minus rk is less than 2r. That means I found one nucleus, might not be the closest one, but I found one that is 2r away from xn. So this means that the right side is also equal to 1 because both characteristic functions are active. Okay, so now here we go. That's essentially the end. Why did I use this inequality? I used the inequality to decouple the A. See, here the A appeared at 2 places. And I want to integrate the A out. Now there's only one A left. This integral we can do. The dA over this. So I'm integrating, right? I mean, this is the same as integrating A when A lives in the ball around xn. So this is just the measure of the ball. Okay? So, blah, blah, blah. Left side is greater or equal. Let me continue here. There was a minus constant z plus a half sum n from 1 to infinity integral. So I told you I integrate out the a. So what's left is the dr over r to the d plus 1 minus plus lambda. What I got from the a integration is just the measure of the ball. Doesn't matter where it sits. And then there is the delta r xn greater than 2r, smaller than 2. Now, the measure of the ball scales like r to the d, so that kills the d. The 1 has the same dimension as the dr, so what's really left of is a length to the power lambda. I'm integrating the r greater than delta r, and therefore this integral just gives me another constant times z plus 1/2 sum n from 1 to n 1 over delta x n to the lambda. That's it. Okay, that was the right side that we were. And I guess I dropped, sorry about that, I dropped this square here. There should everywhere be squares. No. Sorry. No, sorry. The square is only in the stability. Sorry. It's linear here and it's linear there. Good. Good. So that was the proof of this electrostatic inequality. I told you there are alternative proofs based on maximum principles potential theory. They are, I guess, also interesting if you want to look at those, but that has a certain universal flavor, and I think this is really a beautiful formula that is useful in many problems with such interactions. Okay, and so let's answer some questions and then we'll have a break.
So you don't have a square with the...
Yeah, I don't have a square. Okay. It's, I guess morally there is a 1 and a z squared, so everything is sort of like linear. Okay, any questions? You can of course also ask me now, I mean during the break afterwards, and if not, I think we will have a coffee or tea, and then we'll resume in 15 minutes. Right? Good. Version to many-body quantum mechanics. We will return to it, I guess, one more time or 2 more times in this course. But let me now go to the form of the Thirring inequality that is perhaps the more famous or more well-known inequality nowadays. So this is the Thirring inequality for eigenvalues of Schrödinger operators. Okay, and so I mean, for this we need to have some background about spectral theory. I will skip over that to a large extent today and provide the details later on. But just to set up things, so what I'm assuming is, and I'm being here a little bit more general than what is needed, so that we have a real function v on Rd, such a negative part belongs to Lp, where p depends on the dimension. So p equal to 1 is allowed in dimension 1. P is going to be strictly larger than 1 in dimension 2, and p is greater or equal than d over 2 in dimension 3. These are assumptions. What you should think of is, in any case, that I mean, usually I also want to assume p finite, but finiteness of p means that the potential goes to 0 at infinity. These conditions are local conditions saying that the singularities of the potential are not so strong. Then the other assumption on the positive part is essentially absent. I'm just requiring that it's locally integrable. Okay, then under these conditions, minus Laplacian plus v can be defined via quadratic forms as a self-adjoint joint lower semi-bounded operator in L2 RD. Okay, so for those of you who have not, so the issue is that this is not a bounded operator. And for a bounded operator, we know what self-adjoint means. When it's an unbounded operator, then there are some additional things you need to take care of. I don't want to discuss them right now, but eventually there will be something, an unbounded self-adjoint operator. The spectrum does not go down to minus infinity, but starts at some finite number, and that's what lower semi-bounded means. And moreover, p is less than infinity, its negative spectrum consists of eigenvalues of finite multiplicity with 0 as the only possible accumulation point, as the only possible accumulation point. If you want a picture, there's the point 0, there's something going on above 0, and below we have a couple of eigenvalues. I'm usually starting to call the lowest one E1, that's E2. Perhaps this eigenvalue is twice degenerate, I don't know, then I give it 2 labels, and so on. And so you have eigenvalues, either finitely many, or if you have infinitely many, then they accumulate at the origin. Okay. So let En be the eigenvalues in non-decreasing order. Repeated according to multiplicities. Alright, and then we have the following theorem. It's yet another theorem of this Lieb-Thirring paper, 1975. I mean, this is a, I don't know, 2 or 3 page paper in a physics journal, but it's really full of ideas. The inequality says is that d greater or equal than 1, then for any v minus in L 1 plus d over 2, the sum of these eigenvalues is controlled by this norm. The 1 plus d over 2 norm of the position. With a constant that depends on d, but does not depend on v. Okay, so it's a bound on the sum of the negative eigenvalues. I'm taking absolute values to turn the, perhaps I should say this, the negative eigenvalues. So if there are, I'm not excluding that this potential goes to infinity and plus infinity, there might also be positive eigenvalues. Those I ignore. I'm just taking the negative eigenvalues. And so I'm taking absolute values, so you can think of this as a lower bound on the sum of the eigenvalues. Okay, good. That's the inequality that we have, or that they proved. And again, this theorem is, so let me call this theorem 3. I know there was the stability matter theorem that was in between, but the point is that theorem 1, 2, 3, they're all the same theorem. They're all equivalent to each other. Okay? So this is the best constant here. The best constant here is in one-to-one correspondence with the constants in theorems 1 and 2. All right, and I can be a little bit more explicit, although it's a bit hard to remember. Explicitly. If KD, so let's do that. Let's call the constant that we had earlier, let's call that KD. And some En less so-called, this is a real honest inequality, right? V minus 1 plus d over 2 with optimal constants KD and LD. Then, so here comes the formula. 1 plus d over 2 LD, big parenthesis to the power 1 plus 2 over d, times 1 plus 2 over d, kd, big parenthesis 1 plus d over 2 is equal to 1. Okay, that's what I mean by the constants are in one-to-one correspondence. You don't need to remember that formula. I'm just trying to say, if you get this inequality with a good constant, then you get that inequality with a constant related by this, and vice versa. Okay. Now, right, I'm saying the two inequalities are equivalent. How can we guess that? Well, you see these two exponents, they're hurled due to each other. Right, so this is d plus 2 over d, that's a d plus 2 over 2. If we swap them, then it's a d over d plus 2 over d plus 2, that's 1. Okay, so you see somewhere in the background there's a Hurley inequality or a Legendre transform behind that. Okay, and so, I mean, just once again to get the picture, Thirring wanted to prove stability of matter. They wanted with theorem 3, this inequality for the kinetic energy, for antisymmetric functions on R2D, R to the D times N. Okay, now, their first reduction was to go from theorem 2 to theorem 1, where they had the inequality, the Sobolev inequality for orthonormal functions. And the next reduction step was that they went to this theorem 3 for eigenvalues of Schrödinger operators. And that theorem about eigenvalues of Schrödinger operators, that's what they eventually proved. And they proved it and got stability of matter. Okay? Now, why did they do this? Well, because now we've translated into a spectral question, and now we can use tools from spectral theory. There are resorbent kernels, there are heat kernels, there's a Biermann-Schwinger operator, there are trace inequalities. So somehow things have become more linear, and we can use linear tools to do that. And for many, many years, this approach, this from theorem 3 to theorem 1 to theorem 2 was the only way we knew. There was someone, perhaps in the 80s, there was Eden Voyage, who in the special case of one dimension were able to prove it directly or prove theorem 2 directly. But a direct proof of this theorem 1 without going through Schrödinger operators, that was only achieved in 2011 or so, and Michel Rumain gave an argument, and that has become one of the classical proofs that has been improved now in the last 10-15 years. But anyway, so usually people really had to go or went through the spectral formulation that I'm talking about here. All right. What else can I say? Let me perhaps, again, I mean, the equivalence needs to be proved, it's not obvious, but let me give you one direction. So proof of equivalence of theorem, what do I want to prove? 1 implies theorem 3. Again, what we're really interested in when we care about stability of matter is the opposite direction. We want to get from theorem 3, which we actually prove, to theorem 1, but that uses some things about linear operators that I don't want to assume. So let me go assume that we have the Sobolev inequality, and let me show that you get this eigenvalue inequality. And perhaps that gives you already an idea of how you go backwards. All right. Well, for theorem, we want to apply theorem 1. That was the theorem about orthonormal functions. What are the orthonormal functions that are in the game here? Well, they're the eigenfunctions. Right? Okay, so let psi n be the orthonormal eigenfunctions of minus Laplacian plus v corresponding to eigenvalues En. Then what do we have? Well, so this is the sum of the ENs. Right, I'm dropping absolute values, so I want to bound this from below. Now for fixed, let me first, before I do the sum, I can do something very easy. I can just write this as the energy function. Because these functions are eigenfunctions, this thing is equal to En perhaps times the integral of psi n squared, but that's 1. So that's an identity. Okay, for every n. I'm summing over n, and I've got that. Now what do I have at hand? I have at hand theorem 1, which is the Sobolev type inequality. So that theorem tells me that I can bound this from below by this kd constant, this constant here, times rho to the 1 plus 2 over d, where rho is the sum of the squares of the psi n's. Okay. So that's Lieb Thirring for the first term. And then, well, the second term, that is just v times rho, and once again I'm dropping the negative part. It's a little bit similar to this argument for stability of matter that we did. Right? So what we do now is we use Hölder's inequality. It's kd integral rho to the 1 plus 2 over d minus integral v minus 1 plus d over 2. Well, I guess I need a little bit here. So let me break dot is e. Dot is greater or equal. So this is kd integral rho to the 1 plus 2 over d. Minus, now I told you we use Hölder. So here we use this duality of the exponents. Great, so this is, 2 divided by d plus 2 times the integral rho to the 1 plus d over 2 add 2 over d to the d over d plus 2. And now this is greater or equal. And now you see now I'm using once again this inequality similar to what we did before. So there was x minus a to the 2 over d plus 2, x to the d over d plus 2. This is greater or equal than minus a constant times a to a. Similar inequality that we had before, now d is equal, arbitrary before d was equal to 4. Same thing. So we get this is greater than minus constant, and the constant only depends on d, it's the constant of this inequality, integral v minus to the 1 plus d over 2 dx. Alright? And that's exactly the inequality that we have in the theorem. The eigenvalues, the sum of the eigenvalues is bounded below by minus a constant times v. And so you just have to, follow that constant and the constant in that inequality, and then you get that the Thirring inequality holds with the constant L. The best constant is connected with the best constant by this. Okay, this is how this equation is. Okay, and now, again, I mean, you really want to go back and we do this in this course, but today I want to give you more an overview. Okay, so I hope you believe now that this theorem is yet another expression of Lieb Thirring. And so the point of view on the Thirring that we've had so far is a point of view of Sobolev inequalities. Lieb Thirring was a generalization of Sobolev. Now I want to look at the Thirring inequalities from a different angle, namely from the angle of Schrödinger operators in a particular semi-classical analysis mechanic. And so let me, again, details will come later. So, what do I mean by semi-classical analysis? So now the Schrödinger operators that we will look at, they are the same as before, except that I put now a small parameter h bar, I just write h, in front of the Laplacian. Okay, and now the idea of semi-classical analysis, or one of the ideas, is you take a nice function of this operator in the sense of, spectral calculus that we will talk about later if you haven't seen it, and then you take the trace. Okay, so meaning you look at f of the eigenvalues and sum over the eigenvalues of this thing. And then you let h bar go to 0 and you wonder how big is this thing. And the leading order asymptotics says that this is comparable to, so what do we have? Instead of looking at the operator minus h squared Laplacian plus v, you look at its symbol. H squared psi squared plus v of x. That's a function of classical phase space. Now this function f that you've taken of the operator, now you take off the symbol, and instead of taking the trace, you're integrating over classical phase space. Dx d psi divided by 2 pi to d, integrated over rd times rd. Okay, that's one of the key results of semi-classical analysis. Of course, that needs assumptions. I mean, you can prove it if f is nice, usually when v is nice, and there are different techniques of how to do this. It goes under many names. We will often use the name Weil asymptotics. I don't think that Weil ever looked at Schrödinger operators in this context, I think very soon afterwards. So I looked at eigenvalues of a Dirichlet Laplacian, for which you have a similar formula in the same spirit, but sort of it was clear to mathematicians and physicists alike that similar formulas hold for Schrödinger operators as well. And so often we call this wireless. Okay, good. So now, as I said, there will be assumptions, but let's pretend these assumptions are satisfied for the function f is equal to the negative part of e. Okay, it's the function that comes down linearly and is then equal to 0. Okay, and then what we get, so if we take this, then we get, and so what I usually write, I want to put a large coupling constant in front of v. Lambda is now a large constant. This is equal to, like this, the sum of the eigenvalues. Now, because I have these operators that depend on lambda, I'm writing En of lambda to reflect that dependence. And then you see, this is essentially a semi-classical limit. You can just put 1 over lambda in front of the Laplacian. Right, so you use the homogeneity of this function. And you have it here. Now you use your semi-classical analysis, pretend it's true, lambda, and now this integral Rd times Rd. And now what do we have? 1 over lambda psi squared plus v of x. And the point that I want to make now is that the psi integral here can be computed just by scaling again. You change for fixed x, you change variables, write psi as square root of v, I mean the negative part of v square root times a new variable, and then you compute this, and then you find that this is equal to LD. And I write SC for semi-classical times the integral of lambda v of x, negative part to the 1 plus d over 2 dx. Okay, so that's the definition of that constant. And I'm saying, do the integral, and then you get a constant times that. Now, why is this relevant in the context of Lieb? Right? I mean, I can. Some people look a bit puzzled. So what I'm doing here is just that psi squared minus 1 negative part d psi over 2 pi to d. This I'm calling LD semi-classical. That's the integral you have to do. And you can write this in terms of gamma functions if you want. Okay. And the rest then, once you have this definition, then this follows by scale. Good. Now why am I talking about this? The point is, on the left side, you have a sum exactly as it appears in the Thirring theorem, and on the right side, you have an integral exactly as it appears in the Lieb theorem. Okay? It's exactly the negative part of the potential to that power. So, semi-classics gives us some specific constant for which this holds. Lieb theorem says that there is a possibly different constant for which we have a universal upper bound. Okay, but the point, even if Lieb theorem does not get the good constants, you see now we're getting in the territory of constants, even if Lieb theorem doesn't give you the right constant, it gives you something of the right order of magnitude. And that's crucial in many, many applications. Let me write down one application. So let me write it. So LT, even if the constant LD may not be LD semi-classical gives a bound of the right order of magnitude. Let me give you a simple application. The asymptotics star is star are valid for all V minus in L1 plus D over 2, V plus in L1 log. Okay, that's a non-trivial result because I told you when you look at some semi-classical analysis, you do certain approximations, you need some smoothness, some regularity of V. Okay, but here you get it now for everything for which the right hand makes sense. That's the optimal result. You want to establish asymptotics under the assumption that the term, the asymptotic term is finite. Okay? And I mean, think of it as, think from the idea, you know, we all know this Riemann-Lebesgue lemma, right? That the Fourier transform goes to 0 at infinity. Remember how we proved that? We take a function that is smooth. For the smooth function, we can play tricks. In this case, we integrate by parts or something. And we know that it goes to 0. And then we get a uniform bound, namely saying that the infinity norm of the Fourier transform is controlled by the L1 norm. And then putting the uniform bound and the asymptotics together, we get the convergence to 0, the right asymptotics, so to say, for every guy in the class for which we have the a priori bound. That's roughly speaking what goes on here, right? So there are the nice potentials for which we have the asymptotics. Then there is the uniform bound with possibly the wrong constant, right? I mean, we don't care what the constant for the L infinity norm in terms of the Fourier coefficient is. It's some constant that works here, and then we can carry over the asymptotics to 1. Of course, this is much more non-linear than the Riemann-Lebesgue lemma, but the spirit is, I think, the same. You want to push asymptotics established for smooth functions to the general case, you need an a priori bound. Now that, what I was saying, this is so far, this was linear, right? This is theory of linear Schrödinger operators. However, this really becomes interesting in situations where things are non-linear, or where you have non-linearities emerging in a limit. What I'm talking about is the so-called Thomas Fermi approximation in many-body quantum mechanics. This is something, right? I mean, it's no longer on the board, but I told you the formula for the ground state energy of a many-particle system. That's an eigenvalue of a linear operator. It's a huge dimensional space, but that's a linear problem. But in the limit, in a certain limit, we have to be specific what that is, this linear problem can be approximated by a nonlinear problem. Okay, so the high dimensionality of the space gives rise to a nonlinearity. Okay, and when you have something nonlinear, then it is very, very important to have a priori bounds of the right order of magnitude. And that's what Lieb-Thirring gives you. Okay, so Lieb-Thirring is, or this Thomas Fermi limit, is sort of semi-classics in disguise, but sort of in disguise where you don't really know yet the class, because the potential is sort of not fixed. And then it's very important that you have an order magnitude bound that is correct, because that allows you to do all sort of smoothing approximations and so on, and get something out. And you know, people, this is this first result, the verification of Thomas Fermi asymptotics by Lieb and Simon. People have gone on and improved on this result in using higher order terms or doing similar asymptotics in other problems. And it was always crucial to have such ingredients. So even more important or crucial in problems or asymptotic problems in many ways. QM that are related to all asymptotics and I want to mention the G2 as well. Approximation by Lieb inside. And I think the announcement appeared in 1973. Back then they did not have the Thirring inequality, but once again there was a later work which have been greatly simplified using Thirring. My plan is to speak more about this next time to give you some idea about semi-classics, both about the linear, these asymptotics, and about this non-linear asymptotics over here. But for now, I want to leave it there, and now I want to talk about the so-called Thirring conjecture. Okay, so I guess already in this 1975 paper, but then more explicitly in the 1976 paper, Lieb and Thirring made a conjecture about the constants in the inequality. And here's the conjecture that's still completely open now, as back then. This year's the 50th anniversary of this paper. So the KD is, remember up there, so it's a sharp constant. In which was in theorem 1, that is supposed to be, so that's the conjecture. Well, this was a minimization problem, so this is the minimum of two conjectures. There's a KD1 and a KD semi-classical. Right now you don't know what any of this is, and I'll explain that in a second. Before I do this, let me say that one knows both constants, one knows which one is bigger, and that's where we have a dimension non-dependence. In dimension 1 and 2, the one with the superscript 1 is better, and in dimension 3 and higher, the other one with the superscript semi-classical is better. So what are these constants? Where KD1 is the optimal constant in the inequality we started out with today. Remember, there was one function and we controlled its 2 times 1 plus 2 over d norm. X when integral psi is equal to 1. Remember, that was the first inequality we had today. That was the Sobolev interpolation inequality for one function. So the conjecture that Lieb and Thirring made back in 1975 or 1975 and 76 is that in dimension 1 and 2, the constant that works for one function actually works for an arbitrary number of orthonormal functions. What does that mean? Remember my picture at the beginning, I was telling you that orthogonality means that the functions have to go out of each other's way. I was saying that sort of, yeah, they want to spread out to be essentially disjoint. What the conjecture says is they want to be really, really disjoint. So you just take one function to this infinity and another function to that infinity, perhaps a third function to that infinity, that they're really away from each other. And that the overlap is absolutely zero, and that it's the same constant for one function, because they have disjoint support, that works for all functions. That's the conjecture. So it's a very strong repulsion of orthogonal functions. They don't, for this to be good for this inequality, they really want to go away from each other. So repulsion in dimension 1 or 2. What I will tell you now is that in dimension 3 and higher, we will have the opposite. We will have an attraction. They all want to be as close together as possible as the Pauli exclusion principle, as orthogonality allows. Okay? And so there is this difference between repulsion in 1 and 2 dimension and attraction in 3 and higher dimensions, which Thirring predicted and which is not understood at all, neither on a mathematical level nor on a physical level. And I think understanding that would really help us explain what the Pauli principle says in physics. Yes?
I'm trying to think of the eigenfunctions of the Schrödinger operator. In this case, if they were to be optimal for this, the support would need to be disjoint.
Exactly. The potential would have to consist of two bumps that are very, very far apart. And so that essentially the sum, right, that the eigenfunctions are essentially disjointly supported.
Yeah, can we get, with a maximum argument or something like that, get at least one of them? The first is always positive, so the
yes.
support would never be. So
no, exactly, right. I mean, that means that there is no optimizer for the inequality when n is greater or equal than the number of eigenvalues that you have is greater than 2. But of course, there are optimizing sequences. Optimizing sequences are sequences that go very far away because they decay exponentially. Okay? It's a result sort of about the non-existence of an eigenvalue. And so let me write down what KD semi-classical is. So one way of defining it, there are different ways of doing it, but one way of defining it is through this relation that we have up there. You see there? Okay. Is defined by, so there's the 1 plus d over 2 LD semi-classical. We know what that means. That's that constant. That's the while, the semi-classical one. To the 1 plus 2 over d. 1 plus d over 2. KD semi-classical to the 1 plus d over 2 is equal to 1. That's a little bit of an abstract definition, but I'll give you now a way of how to think about this concept. Okay, and that will in particular explain that this really is an attraction phenomenon in dimension 3 and higher. Okay. First. Okay, here we go. More intrinsic definition of KD semi-classic. And what I'm doing here is very heuristic. And as I said, I will be more precise next time, but I just want to get you an idea so far. And so the function that I want to consider are the following functions. E to the I psi of x, there's a 2 pi L to the minus d over 2. X I consider in R modulo 2 pi Lz to the d. Okay, so these are functions of x, and psi is the parameter. So the parameter psi is the one that replaces my n. Okay, and so I take a finite number of those. So this is 1 over L, Lz to the d with psi squared less squared. Now what is, okay, so I've written down functions. These are functions of x, and they are parameterized in a discrete fashion. And the constant is supposed to be independent of the number of functions that we're taking. Right? I mean, these are finite, there's a finite number of constants. Now, of course, what is the thing that what is heuristic about this argument? What's heuristic is that these are not functions that are defined on Rd, but these are functions defined on the torus. Okay? I mean, the thing that is okay is that these functions are orthogonal to each other. That's fine. And they're orthonormal, or they're normalized also. So that's fine. I ignored boundary issues. So this you can fix in one or another way. One way to do it is look at signs. Okay, then they go to 0 at the boundary, and you take the right signs, and then in the bulk you don't see a difference. Or another way is you multiply these functions by a cutoff function that essentially lives at scale L. Okay, that gives you an additional term from the localization that you have to argue away. Or there are also some more clever tricks to do it. I want to talk about. I don't want to talk about it now, but I will discuss it in detail how to do this. But for now, just think of these functions, okay? Because that's, I think, the best thing to get the idea. So what is density? So the sum of the squares. So I'm writing n, but this n index is really this psi index. So that's the sum over all psi in 1 over L z to the d. What do we have? Well, we have just the absolute values of these functions, right? Which is just 1 over 2 pi L to the d. So this is the number of such psi's divided by 2 pi. And what is the kinetic energy? Gradient of psi n squared. That is equal, one can differentiate that, and you see you get down a psi, so this is sum, same thing. I guess I forgot to write the constraint, psi squared less equal than mu, psi squared less equal than mu, and now we get a psi squared 1 over 2 pi L to d. Okay, and now what you do is you make a Riemann sum approximation. Okay, and the Riemann sum approximation says that this will become, and so there will be a limit, there's a limit mu L squared going to infinity, where this integral, and I might not have the right asymptotic coefficient, but the important thing is this is psi squared less or equal than mu d psi. There's probably 2 pi d missing, and here we just have the integral psi, same as a term psi squared less than mu d psi over 2 pi d. And so therefore, so I did not tell you what this is a coefficient, and so the constant kd semi-classical is equal to the constant psi squared less than 1. Again, by scaling, I can set this equal to 1 divided by integral psi, integral simply psi squared less than 1. Okay, so once again, what do we have here? We're drawing the lattice, and we're taking these points with a very small spacing. The spacing is between the points is 1 over L, and the radius is square root of mu. And the limit we're interested in, this is where mu times L squared goes to infinity. That's the limit where you have many, many more points in there, where they essentially become a continuum, and where all the sums, like this sum and that sum, become integrals. And that is, I mean, you can do this, I mean, this is a limit, and this is a limit, and then this is a valid trial configuration, so we do know for sure that the Lieb-Thirring constant has to be greater or equal than this constant that I construct in this way. But the conjecture is that in dimension 3 and higher, this is sort of the optimal configuration. That's the best you can do. So these functions, these orthonormal functions, want to become these plane waves with a constant density. Okay. Good. I mean, it's not really clear when you see it for the first time that this constant that you get in that way is related to the constant of while by this formula. Right? That's not, I mean, of course you can compute this constant in terms of gamma functions, and then you can compute this constant in terms of gamma functions, and you can compare the gamma function and you see that they're equal. That's a little bit, that's not a very satisfactory argument. I guess you see some intuition because you have a phase space integral here, and you have more or less a phase space integral here, where just, I mean, the fact that the integration over space is trivial. But anyway, this is all the things that we will discuss in detail. So now I'm coming to the end, and I want to present some recent results. On Lieb-Thirring. So these results are in a different direction. The one way that people go is they want to get an as good or as large as possible constant k. Right? Because that will give you a better constant in the stability of matter. And so that has been a continuous improvement, and the currently best result is from a joint work with Lieb, Lieb, and Nam, Munich, and there we say for any d greater than 1, the kd constant is greater than 0.4719 to the 1 over d KD symmetry 6. And so if you want to have this in particular, if D is equal to 3, then this is about 78%. I think it's 7785, if I remember well. Yep. K3 symmetries. So that's the constant that enters stability of matter. Lieb and Thirring conjecture that you should have a 1 here, well, at least with 78% we have. Okay? And that you should look at this as an improvement to be compared with what did Lieb Thirring have originally, LT's, so sorry, that's a 3, K3, they had about 18, 0.1853. Okay, so from 18% we went up to 78% in these 50 years. There were many results along the way. Lieb himself improved this several times, got better and better. There is an important work by Jean Dambou and Michael Loss and Adi Laptev, which I guess, yeah, so this result is, I think it was published 21, not so long ago. Many intermediate results. And so before ours, this was by Sean and Michael and R, who used this idea of Eden-Feuersch that I was mentioning, and it's sort of interesting that these proofs, both this proof and that proof, really are based now on this idea of theorem 1, about the Sobolev inequality idea. Remember, I was making this point that Lieb and Thirring had to go this complicated way to go to Schrödinger operators because then they had all the good tools, but nowadays things have turned around slowly, and it's this Sobolev type inequalities that people have used to get better constants. Okay, and so this term is obtained by the improvement of the method that Michel Romain suggested, plus ideas of Henri Poincaré and Thirring. But that will be one of the results, for instance, that I will explain in this course. Now, of course, you can say, well, now the constant is better and the constant in stability of matter is better, is good, but we're not any closer to this Lieb Thirring conjecture. And to understand this repulsion attraction dichotomy depending on the dimension. And there has been one result, I think, where something like this was verified. So let me introduce note KDN, note the constant in theorem 1 restricted to less or equal to n functions. We have these orthonormal functions, and then we have a constant, and the main point of Lieb Thirring was that there was a constant that's independent of a. But you know, I can do mathematically, I can look at a constant when I'm allowing at most n functions. Okay, let's look at that constant. That's the best constant with that machine. Okay, now what do we have? Now clearly, of these constants, it's greater or equal than KD, so it's a minimization problem. So if we allow more constants, then possibly the constant has to go down. That follows just by the definition. And then, of course, the constant that works for any function, any number of functions, is the minimum, which is asymptotically achieved. That's a Lieb Thirring constant. Okay, so that's true. Now here's a theorem. and this was obtained jointly with David Gontier, who's some of the audience up there, and Mathieu Levine. And I mean, we obtained this, I think, 4 years ago, but it's still not published. It's accepted in the American Journal of Mathematics, and we're waiting. I guess this result actually we had in a previous paper, but we didn't stick to that. So what we have there is that d greater than 3, and that's of course the important thing here, because we want to see a dimensional dependence. Then there exists a sequence nj tending to infinity, such that this inequality is strict along that sequence. And so that we interpret as a sign of attraction. Because we do want to have more and more particles, really more and more. Right? The constant goes strictly down. It's better to have more. I mean, this is far away from the conjecture. I mean, I'm honest about this. The conjecture says something about plane waves that we should get. We don't know that. But at least we seem to see some attraction phenomena. The assumption d greater equal than 3 appears in our proof. It goes in crucially. I mean, of course, the fact that we cannot prove for dimension 1 and 2 does not mean that we don't have repulsion, an attraction there. It could be that we just have the wrong proof, but at least it's a good sign. And if you look at the mechanism behind the proof, it might really be that there is some understanding here of what is behind the Thirring, but it's not the final word by far. So this is justifies attraction in d greater than 3. And then to finish today's lecture, there's another theorem which appeared on the archive this morning by Chaire, Denzler, Jean, and Thirring this morning. And so what they argue is that d equal to 1, right? Dimension 1, that's the regime where we expect repulsion, where they should go away from each other. Then k1, 2, that's a constant where you allow two functions, is equal to k1, 1. That's in the spirit of Lieb theory. Okay? That says that the two functions want to go infinitely far away from each other so that you only have one constant there. Okay? So this justifies repulsion in the okay. And what they use is a reformulation of this Lieb-Thirring problem for two functions that's due to Ben-Guria and Loss. It's called the ovals problem that was done perhaps around 2004, I don't know, and they were able to reformulate this into a geometric problem which has attracted the attention of many people since then. So even in geometry, this is a nice question about ovals. Many people have gotten results in constants here throughout the years, but as far as I understand, it's a control theoretic approach that they use to finally settle this conjecture. And of course, the new thing, what happens if you have 3 particles or more? That's the next step towards a Lieb-Thirring conjecture. But I think for today, I'm done with the lecture. Perhaps we stop the recording now, and then you can ask questions offline if you want. And we resume next time when I flash in some of the details that I left out. But I wanted to give you an overview of what we will do in this course. proofs, right? I mean, the theorems all have proofs, and you will see the proofs. Okay?